SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. Every human being is spiritual in heart by birth, and that we will when we go along with modern life. Let us now recall what we learnt in the last lecture. In the last lecture, we started discussion on how does the specific volume vary with that time, and little qualitative way we looked at, and we defined various time like your residence time for gas phase reaction, ignition delay time, and these two times are known as the total residence time for a non-hypergolic propellant. In case of hypergolic propellant, we also define two time, one is liquid phase combustion time and gas phase combustion time, and some of these two are basically residence time. And later on we moved into the discussion about the combustion chamber geometry, how it is important for ascertaining the completeness of combustion, and we also looked at little phenomenological analysis and tried to relate this the characteristics length and to the residence time. Ratio of characteristics length and characteristics velocity is a function of both the time, that is ignition delay time, and the gas phase, that is the residence time. But we try to relate those things and find out a relationship which can be utilized for design purpose at least. And then we looked at some data of the characteristics length, and then we conclude that characteristics length is dependent on the type of propellant, and also before that we discussed characteristic length is dependent on the injection system. And when you talk about injection system, there are several parameters which comes into picture. Those parameters are the pressure drop across the fuel, oxidizer, type of propellant, type of injectors, injector distribution, turbulence level, and so on and so forth. So, therefore, it is very important to look at the characteristics length, and which is being generally used for design purposes. And today we will be discussing about basically what are the shapes of combustion chamber we can have in case of liquid propellant rocket engines. There we have decided the characteristic length. From that one can really find out what is the length of the combustion chamber, and however what will be the shape. Of course, in your mind the cylindrical shape will be definitely there. So, let us look at the cylindrically shaped combustion chamber, which is having certain length, and if I consider this is your LC, and this diameter is having basically DC, that is your diameter of the combustion chamber. So, this shape is a cylindrical in nature, and which is generally being used, and that is the common thing to be used. Keep in mind that for a particular combustion chamber volume, I can have a smaller diameter, and then the length has to be increasing. If the diameter is less, then of course the surface area will be higher, and then heat transfer one has to look at it, and if the length is more, then the pressure drop will be higher. And however, this smaller diameter combustion chamber of cylindrical in shape can really withstand the high pressure and gas, so that the thickness requirement of this cylinder will be lower as compared to the bigger diameter combustion chamber. And there are several parameters which will be affected by the proper selection of the combustion chamber. In other words, the shapes of the combustion chamber affect the pressure losses, as I told, and so also the heat transfer, because the heat will be transferring through the wall and also this thing. So, this heat transfer also will be affected by the shape. And combustion instability, the length is higher, people say that the maybe it is subjected to some axial oscillation of the pressure, and then one can get the combustion instability, and the length will be higher, the weight will be higher, and also the reliability will be good provided the smaller diameter. So, that this thing, and if when the length is higher, then the cost also will be higher, and so also. However, the diameter is bigger, then the drag of the engines may be higher. That depends upon what is the range with which one can operate. So, this is the cylindrical combustion chamber which is being used profusely at this moment across the globe. But there are several other shapes one can think of. One is the spherical combustion chamber, and spherical combustion chamber is basically the one which I have shown here. It is having higher surface to the volume ratio, and so that the space utilization will be very good. However, it is having the problem is that how to mount this injector, because the curved surface, one has to struggle to have this manufacturing, and also design changes has to be made. But here the major portion of this combustion length, if I consider this portion, right, kind of thing, this is your combustion length, right, and then that will be major length of this combustion chamber will be filled with this atomization and vaporization the process, and very less time will be available for the combustion to take place in this portion. So, this portion will be basically combustion which will be taking place, and this is vaporization and atomization. So, as a result, the complete combustion may not take place, and beside this, it is difficult to fabricate this shape. However, it can withstand high pressure because this is spherical in nature, and manufacturing wise it is quite difficult. The German people had used this kind of spherical combustion chamber because of this inherent problem of manufacturing and incomplete combustions. Therefore, they abandoned this idea, and some people have now combined this spherical combustion chamber and cylindrical combustion chamber, come up with a new one which is known as near spherical combustion chamber, which is having a certain spherical portion of this thing combustion chamber. But however, it is having a flat head, which is this is a flat head, where the injector head can be placed very easily without much problem. And here the length has been increased little bit for the same volume one, such that one can get a little larger residence time as compared to the spherical one, and so that the combustion can be more efficient, and then ensuring the better performance. Beside this, you can have various other things that can be diverging portion. There can be also the combustion chamber with a throatless nozzle. So, there are various varieties one can think of using that, so that can be, and the shape of the combustion chamber will be depend also on the imagination of the designer, and also the requirements at the hand. So, therefore, one can really find out various ways and means of, that is the beauty of engineering, where you can have a lot of luxury of innovating and then making a new systems, so that it can be more efficient and amenable for better use. So, let us now look at the most important components which will be supplying the propellant to the combustion chamber, that is propellant feed system. Propellant feed system, if you look at, is very important, as I told, because this is required to inject the liquid with the help of high pressure gas or high pressure system. So, the as I told that it is very important to have a proper feed system such that the pressure losses will be minimized. At the same time, you can operate for a longer range, and you can have also the high pressure such that atomization can be efficient and effective. So, depending on the type of system being used, the propellant feed system can be broadly divided in two categories. One is the gas feed system, other is turbo pump system. In case of gas feed, we use the high pressure gas to pressurize the liquid propellant, and which can be injected into the combustion chamber through the atomizer. And let us look at a typical gas feed system, in which case the high pressure gas being used in this tank, and generally the nitrogen, helium, argon gas are being used, which are inert in nature, and this will be at a high pressure tank. This is high pressure, the gas which will be stored. And then through this flow regulator and also the pressure regulator, there must be also the pressure regulator, which must be used such that the constant pressure can be maintained at the downstream of the this valve, such that the liquid can be expelled into the combustion chamber at a constant pressure. Keep in mind that this is the gas which will be coming to this, and there might be a separator, a diaphragm kind of thing, or a piston which is being used, and that will be forcing the liquid into the expel into this cylinder, and this is your injector head, and then there might be spread, and this is similar things will be also used for the liquid line. This is your liquid fuel line. And keep in mind that this gas feed pressure system is generally used for smaller thrust level rocket engines, as the duration of its operation will be dependent on how much gas is being stored, and also if the thrust is higher, then naturally the pressure of the injectant will be much higher. So, therefore, the pressure which will be requirement will be higher. As a result, this may not be good for the high thrust and long duration rocket engines. And another one is basically known as the turbo pump feed system. In case of turbo pump feed system, what is being used is that liquid oxygen or the fuel or the liquid oxidizer. It can be oxygen, it can be also the oxidizer, and in this case the in place of high pressure gas tank, the oxidizer pump and the fuel pump are being used. Generally the centrifugal pump are being preferred over the axial one, and keep in mind that this has to be now this pump had to be run by some external device, like generally the turbine is being used, or people can use also motor, but in rocket engines we cannot have that electrical energy to be used, therefore, we use a turbine. And for that you need to run the turbine, you need a gas generator. We use this oxidizer and fuel and burnt in this. This is your gas generation or a combustion chamber to produce some gas which will be passing through this, and it will be generating the power, right, and then of course, it will be expanded and exhaust at the exit of this turbine, and then this power will be transferred through the gear box to this fuel pump and the oxidizer pump. And keep in mind, to start this liquid turbo pump system, we need to have certain amount of high pressure gas such that you can start and initiate the process. Later on, the turbo pump system will be running of itself once the turbine is started running. So, this is the basically the gas feed system and turbo pump feed system what is being used. If you look at each component are quite complex. I have just shown in a schematic diagram, but it's really the turbo pump system needs a lot of mechanical components like your pump. In the pump itself, there will be several various component, impeller, diffuser and several other things, and the bearing, shaft. This is your shaft, as I told, gearbox, and then combustion chamber, and several other components which are not being shown like a pressure regulator, flow regulators and several components. So, turbo pump system is basically quite complex and intricate to design and develop, and as compared to the gas feed system. Therefore, the gas feed system is used for a smaller and short duration liquid propellant rocket engines. So, let us now classify the liquid feed systems. If you look at liquid propellant feed system based on the pressure level what is required, we can have the gas pressure feed system, and then we can have the turbo pump feed pump systems. And gas pressure feed system again divided into three categories. One is high pressure inert gas, as I told, nitrogen, argon, helium and can be used. And there is another one which is known as the vaporized propellant gas. That means you just use some liquid propellant and vaporize into due to using some heat or some other process, so that it can vaporize and the pressure will be increasing in a closed chamber. And there is another one which is used known as the chemically generated gas, and this chemically generated gas can use either the solid propellant or the liquid propellant. So, one can say that solid propellant gas feed system, in which the solid propellant is burned and the gas being produced in a constant volume chamber, such that the pressure will build up and that can be utilized for pressurizing the liquid propellant. And similarly, you can have a liquid propellant gas feed system, liquid propellant gas feed system, gas pressure feed system, right. So, I can write down GPFS. And turbo pump system can be again divided two categories. One is pump, other is turbine, and pump can be of multi-stage impeller, it can be single stage impeller, it can be two stage impeller, it can be three stage, various stages can be used depending on the pressure level requirement. And turbine, it can be hot gas turbine, it can be chemically generated gas turbine. And these turbo pump systems can be divided into various categories, and we will be discussing three of them. One is gas generator, other is your stage combustion, and the third one is your expander type turbo pump systems. So, therefore, one can also divide this gas liquid feed system into various categories only due to the paucity of time and complexity. I will be not discussing about them. So, let us now look at a question might be coming to your mind, what are the advantages of the pump feed system. So, advantage one is better flexibility in operation, and like your gas pressure feed system, once it is operated you cannot really change. You can control the flow rate, you can have a better flexibility in operation, and you can get a very stable pressure range. But in case of the gas pressure feed system, whenever the pressure of the gas chamber will be receding, then the pressure will be falling down. Of course, the pressure regulator will control the pressure to some extent, not beyond certain point. And also the smaller volume requirements is really can be made for the turbopump systems, particularly for higher thrust level rocket engine, and you can have a higher power to weight ratio for a turbopump system. So, therefore, the turbopump system is being used particularly for high pressure, high thrust level rocket engine for longer duration. And keep in mind that in the gas pressure feed system you can be hot gas pressure system, because by heating it will be its pressure can be increased such that you can have a compact and better pressure feed systems, which will be not discussing at length, but maybe I will little bit talk about it while analyzing that. So, let us now look at the analysis of the gas pressure feed system. We will be using a very simple analysis, and let us consider a typical gas pressure feed system. So, there will be a gas tank where the inert gases are being stored at a high pressure. Let us say this is P naught is your initial pressure, temperature T naught is the initial temperature of the gas in this high pressure gas tank, and the mg is the mass of the gas which is stored in the initial state. And there is of course at a certain pressure regulating valve, and also this is on and off valve or the control valve, and this is your gas feed line. Keep in mind that this is a liquid which has to be pressurized or pushed through the rocket injector such that it can be atomized. And in this free volume where the gas will be coming and trying to push this diaphragm or a piston, whatever it is being used, that pressure or the pressure will be remaining constant, that is Pp. And when this pressure regulator and the on and off valve is open, and then the gas will be pushing this to that pushing this gas and liquid into the atomizer, and let us say that at the end of this supply of this propellant, the P naught will be coming to that PR, and this I call as basically residual pressure. Residual pressure is that, and T naught is your T residual temperature, and beyond this residual pressure one cannot really operate it, because the pressure regulator will not work below this. So, TR is your residual temperature. We will be now analyzing it, and the design requirement is that low molecular weight gas will be using high gas density, and minimum gas weight should be and high stress density ratio. That is the design requirement one has to meet, and while designing this gas pressure feed system. Let us now look at how we can estimate the pressurizing gas mass. So, for that we will make some assumption, and we will consider the gas is behaving as an ideal one, and in this case we are saying that the mass in this pipe is negligibly small, and let us consider this is your system. This is your system in this thing. This is a cylinder, this is a cross section of the cylinder I have shown you and in a two dimensional figure, and keep in mind this is my system. And if you look at the gas will be getting into this, and then of course the pressure downstream of this pressure regulator will be remaining constant. So, we are not bothered. And to start with, the energy which will be there in this gas tank at the condition of T naught, P naught, and then amount of gas is mg at the initial state, or the time is equal to 0, you can think about that. So, the assumption we can make basically, one is that your ideal gas law, and we are considering the adiabatic process, no heat being transfer, although the gas is expanded in this gas tank from higher pressure to the lower pressure. Keep in mind that PR will be much lower than the P naught, and so also the TR will be much lower than the T naught. And other assumption one can make is that the mass in the pipe is small, quite small, to be neglected. So, what we will do, we will basically look at energy balance, as we know that gas stored in this tank at a higher energy level, and then during expansion it reduces, and that energy utilized to expel the liquid propellant at a high pressure into the combustion chamber. So, by invoking first law of thermodynamics to this system, we can have basically change in internal energy between the two states. One is the initial state, other is the final state, that is when it will be attaining the residual pressure and residual temperature, is equal to basically dW. Keep in mind that the energy will be reduced, therefore, the change in internal energy is negative, and this is your work done. This is your work done by the gas, and this is your internal energy. U is your internal energy change. So, this equation we can call it as a basically equation 1, and if you look at, I can write on this as basically U2 minus U1, right, is equal to what is your final energy which will be there, that is the sum of the internal energy of the residual gas. The internal energy of residual gas, if you look at U2, will be consist of internal energy of residual gas Mr CVTR. This portion is basically internal energy of residual gas plus the internal energy of the propellant tank, that is because the gas is coming in out, that is MP during this operation into CV into TP. This is your internal energy of the thing. So, therefore, we can write down this m r C V T r plus m p C V T p minus U 1 will be the initial internal energy of the gas in this pressurized tank. So, that will be m naught C V T naught is equal to basically the work done, that is P P and V P, and V P is your volume and P P is your propellant pressure, which will be achieved by this gas tank. That is the work done by pressurizing tank in expelling the propellant, that is P P V P. So, I can say this is your equation 2. By your ideal gas, we know by using ideal gas law, we can get M P is nothing but your P P V P, that is the volume, into this R is your specific gas constant, and T P. Similarly, I can also find out M R is nothing but P R V naught, that is your initial volume V naught, which is remaining constant as such, and this is R T R. Now, I can write down this equation 2 as that is your M R. In place of M R, I can write down P naught V naught R T R C V T R plus M P is equal to P V P R T P C V T P minus M naught, and I can write down this plus P P V P is equal to M naught C V T naught. Keep in mind that I can cancel this out, I can cancel this out. Now, I can divide this thing by C V T naught, C V T naught, and also 1 over C V T naught. So, if you look at this, cancel it out. Let us simplify a little further, and then I can write down this is your P R V naught by R and C V, and I can divide it by C V T naught. So, this C V will be cancel it out, and then I can write down this P P V P R C V into 1 by C V T naught. So, this will cancel it out, and plus I can write down this is P P V P and C V T naught. I can make it in the numerator denominator both R, and keep in mind that this is equal to M naught. So, I can look at this now. The M naught I can write down as if you look at, I will take this P P V P and R T naught common. If I take this P P V P R T naught common, I will get here in this term, this is nothing but your R over C V, plus if I consider this P P V P R T naught, this will be 1 plus this term, what I will be getting is P R V naught R T naught. Keep in mind that the V naught is basically by ideal gas law R T naught, M naught R T naught divided by P naught. So, if I put this in place of V naught here, if I will put this m naught R T naught by P naught, this R T naught will cancel it out, and I can take this term into the left hand side, then I will get m naught is basically 1 minus P r by P naught is equal to, and this keep in mind that this is nothing but your gamma, we know from the ideal gas law. So, therefore, this will be P P V P by R T naught, this is basically gamma. So, therefore, we can write down m naught is P P V P divided by R T naught gamma 1 minus P r divided by P naught. This is my expression 3, and this is the expression for the mass of the pressurizing gas that must be stored in the gas tank. So, if you look at this equation, there is a one term here, at what indicates is that this is the mass of the gas required to be expelled isothermally. This is isothermal expansion, and this is the pressure through which adiabatic expansion will be taking place. This is basically, this term is adiabatic expansion. Keep in mind that neither the isothermal nor the adiabatic expansion will be taking place, but we have considered this analysis to be ideal and it will be in between rather. And if I consider this R instead of R, I can write down RU by molecular weight. So, you can find out that m naught is basically will be decreasing when molecular weight of the gas will be decreasing. That means, if we use helium in place of nitrogen, then naturally the mass of the gas for will be reduced for providing the same pressure level, and the mass of the gas for the providing the same pressure level also will be reduced when the T naught is increased. Therefore, that means initial temperature can be increased. That is why the hot gas pressure tank is being used. That means, one has to heat the gas pressure by various means, which we will be not be discussing. So, therefore, with this simple analysis one can really find out the what is the mass of the gas that can be stored, and then this portion is for this term is basically the mass of gas required during the isothermal expansion. So, with this I will stop over, and in the next lecture we will be discussing about turbopump heat system by considering an example. So, thank you very much.